Welcome to this video on applying Gauss's law, and in this video and a few others I'll be looking at using Gauss's law to determine the electric field around different charge distributions, and in an effort to keep the videos a little bit shorter I'll split them up into the different shapes. Now the most important thing is not to memorize the equations, but rather learn the process by which you can come up with the equation. So if you're presented with a shape that you're not aware of or a distribution that you haven't seen before, you still have hope of figuring out the electric field. So that brings me to probably the most important point, and that's the big picture, is that we're looking at a method, right? And the method that we looked at before, method for determining the electric field, is the brute force calculus method. That's what I was calling it, but it was a little bit cumbersome sometimes because one, it takes a lot of time and steps. Two, it takes a lot to set up the integral that you need, and then third, if you don't know the calculus identity or you can't identify what form the integral's in, then it can actually be really hard to even solve the integral. And so this method isn't always the best choice, and when it's not, we use Gauss's law. Now Gauss's law is also a calculus method, but it is, because of its ingenuity in how it looks at a situation, it actually makes the calculus part a lot easier to solve. But there are some very important steps into setting it up so that it can actually do what you're wanting it to do. And so what we're wanting it to do is, for this first example, we're looking at a line of charge here, or maybe even a rod of charge in this case. And this is what we're going to want to find, is maybe the electric field right here, or maybe even right here. And let's actually pick that asymmetrical point so you can see that it does work kind of for any option, and it doesn't really make it more difficult like it did in this method. So Gauss's law is employing the tool, right? So you want to think of this as a tool, or the concept of electric flux, symbolized here with phi sub E, and it equals, remember, two different expressions. One was the amount of electric field passing through a specific area, okay, and here we're looking at an enclosed area. And then Gauss added to this by saying that it's also proportional to or equal to the amount of charge that's enclosed in that area divided by the vacuum permittivity constant. And so we're going to use this idea in order to figure out the value for the electric field at that point. Now, what's important is, one, being able to read this, but two, being able to actually apply it, and it takes a few steps. So the first thing that we need to do is we're thinking about, okay, I'm enclosing a certain amount of charge in a specific area. So the first thing I need to do is I need to choose an appropriate Gaussian surface to enclose the charge distribution. And now what I'm going to do as I go throughout the video is I'm going to copy and paste these little notes in so that if you want to screenshot afterwards, you can have them all concisely together. So choose an appropriate Gaussian surface to enclose the charge distribution. Now remember, the Gaussian surface is imaginary, and that's what's really important. Okay, it doesn't actually exist outside of our abstract mind in order to answer this question. And the key word here, of course, is appropriate. So what constitutes appropriate? And I have another little blurb here that I'm going to copy down over here. What constitutes appropriate? Well, the imaginary surface must be a surface where the electric field is constant along that defined surface. Okay, and the reason for that is because if this were not constant, then you'd have to integrate a function in as part of this, which sometimes you need to do, but it's easier to just pull it out, and then you don't, then you're just integrating the shape, which usually is just the formula of a specific shape. So we want to get a shape where the electric field is constant on the surface, and then we'll be able to pull it out. So where is this constant? This will mean that the surface has to be similar to the topography right, or the terrain of the surface of the object. So if you think of this as being a rod, although I've kind of just drawn it as a rectangle, think of this as being drawn a rod, it's got rounded cylindrical kind of curves, right? That's probably what the surface is going to need to look like. And if we think about why that is when you're thinking about the distance from the surface, right, that's one of the most important things that determines what the electric field is, right, is how far away from the source it is. Okay, so how do you know where to start? You know, how do you even know where to start when you're trying to choose a surface? Well, I have a rule that I kind of use, and that is I usually try to pick the point and then trace a line or lines where the value of the electric field would be the same at all points on that line, and then I'll do that on all sides of the object. So here's what I mean. So here's my point, and I'm going to choose to sketch a line, okay, or even if you have to start with a series of dots, so I would say, okay, well, the electric field's the same there, it's the same distance, same here, same here, same here, and you can kind of, you know, just talk yourself through and say, okay, well, it's the same all along that line, and then it says do so on all sides of the object. Obviously, this is just a two-dimensional representation, so obviously, you know, you could come out of the screen, but I'm going to say the same distance down here. I'm just approximating that right now, and I would say, okay, yeah, all along this line, the electric field is constant. And if I think of this three-dimensionally, it would be over here, you know, in front of this as well. So at this point, the shape should start to become apparent. And if it's a regular geometric shape, all the better. Okay, so what I'm seeing is if I actually kind of sketch in this line now, just kind of imagine it should be straight, I would be starting to think about, it would be like almost like a piece of paper wrapped around here, and it would actually be a cylinder of some sort, right? And so we'd be able to have this cylinder that is enclosing this shape. Now, an important thing is you don't have to enclose the entire shape. You only have to enclose a portion of it or a part that you're working with. So that's why this Q here is really important. It's only talking about the amount of enclosed charge, not all of it, right? All right, so now what? Well, we're going to draw electric field lines from the charge distribution. Okay, so from the rod. So I'm going to draw my electric field lines. Go ahead and do that. And I didn't tell you this one is a positive rod. So that would mean that the electric field lines are going to point like this, right? And they'd be coming off on all sides, but I'm just drawing obviously two-dimensional here. Okay. The next thing is to identify which parts of the imaginary shape have zero or maximum flux. Okay, sometimes all parts of the shape will have the flux, but sometimes not. And so what that means is, remember, that the maximum flux is when the area, right, is parallel to the electric field. So what that, remember, area vectors point normal to the surface, right? So basically, anywhere on the roundish, this like sort of round sheet part of the cylinder would have maximum flux. But these end caps here, the area vector actually points left to right like this, right, for each end cap, and that area is at 90 degrees to the field lines, and so it doesn't count, right, because it would come out just to be zero flux. So at this point, what I've done is I've said, okay, the region of, or the portion of my shape that actually matters is just this cylinder shape and not the end caps, these circular end caps, okay? So next I'm going to identify the formula, so to speak, for the surface area of the imaginary shape, but only for the surfaces that have non-zero flux. So if I was figuring out the entire surface area of this, I'd have 2 pi r, right, for the circumference, times the length, and then I'd have to say plus pi r squared plus pi r squared, right? But because these two ends don't matter, they don't have any flux, then I'm going to leave those out. So the only part that matters, right, the surface area that matters is 2 pi r times L. Okay. Next, we're going to use this later. So next, we're going to define the charge density as uniform or non-uniform. Okay, that's the charge density of the charge distribution, and then write an expression for the enclosed charge. Okay, so what I'll do then is say, well, I'm enclosing, and I'm just going to define this as Q amount of charge, so I'll say it's Q, and I'll go ahead and I'll use the linear charge density, and then length, of course, is the amount of length that is enclosed. Okay, the more length I enclose, the more Q I enclose, but for here we're just looking at this small piece. Okay, so I'm going to use those later, and now I'm at the point where I'm actually ready to integrate. All right, so when I'm ready to integrate, I'm going to start with my Gauss's law expression here, or the flux expressions, and I'm going to say integral E dot dA is equal to Q enclosed over epsilon naught. First thing to do is to say E's constant over this entire surface I'm about to use, so I'm going to go ahead and pull the E out to one side, and then, or outside the integral, and then I can write this, right? And next up, I'm going to do the integration. Well, this is just adding up all the small, tiny little pieces of area and summing them all together. And so when I've done that, I'll get the surface area of the cylinder. So I'll be left with E times 2 pi RL, okay, equals Q enclosed over epsilon naught. The next thing that you can do here is you can stop and say, I'm just going to isolate E. Okay, so let me go ahead and do that. So that would give me E is equal to the Q enclosed over 2 pi epsilon naught times R over L. But what's usually more useful than having this set amount of Q is to rather put in this expression over here. Okay, so I would do lambda L over 2 pi epsilon naught times R over L, and then what I can do is get rid of the L's, and we see that the length of the rod actually doesn't even matter, right, in determining the electric field at a specific point, which makes sense. And so what I would say is lambda over 2 pi epsilon naught times R is the function. Okay, so the function is this that I just said, and so when I look at that, right, this R value, it says basically that the further out I move from the charge distribution, this line of charge, the weaker the electric field will actually end up being. And so I have an expression here that can be used for multiple values of R. Now, something that's important to note is that on the ends, right, there's going to be these end effects that happen where the field will start to not point, the same that it had been in different places. So it would be slightly different on the ends here, but we're looking for a pretty long line of charge and just like the electric field along, the kind of the middles, if you will, of it. But there you go. That's the main process. And if you employ the steps that we talked about, then it will actually be a lot easier than just trying to memorize each shape. So in subsequent videos, we'll take a look at a few different distributions and how to choose the shape.